Welcome to it, grade 11 Mindsetters. It is your time for physical sciences, and you're hanging out with Looney and Tracy. How are you, Tracy?
Good, and you?
It's been forever.
It does seem like it. Where have you been? I've been here. Where have you been?
I've been multitasking with the other days and all the
Fun.
other.
It's okay. You can like that.
So what are we doing for the grade 11s today?
Today we're going to start our acids and bases series. We're going to do this for 3 weeks. We're very excited. But today we're going to lay a bit of foundation, do some what's the word, terminology, do some definitions, basic stuff. So it's compared to some weeks, it's quite a nice
chilled session.
Chilled week. Yeah.
Okay. Grade 11s, you heard it's a chilled. You saw Tracy, she's like, it's a chilled lesson today. You're just doing the foundations of acids and bases. Remember to hit us up on Facebook. Our page is facebook.com/learnextra. You can also follow us on Twitter, and we'll follow you back at learnextra. And you can download the show notes, the videos, the schedules on learnextra.co.za/live. So with all that said, I hand it over back to Tracy.
Oh, thank you, Lee. Okay, well, guys, as I said earlier, we're doing acids and bases, which is really nice. And what we're going to do today is we're basically going to look at the properties of acids and bases. Shouldn't be anything new, hopefully, because you've been doing this since grade 9. We're going to list some of the common acids and bases. It's really, really important that you know their formulas. We're going to do some definitions of acids and bases. There's actually a couple. And we're going to talk about why we don't use them, why we don't use one anymore. We're going to talk about why we do use the others. We're going to discuss the concept and look at conjugate acid-base pairs. That's really, really important. And we're going to discuss the concept of an amphibolite. So we're really just laying the foundation, doing some basic work. In the next couple of weeks, we'll look at titrations and calculations. But today, we're just really laying a foundation, okay? So the first thing we need to do is we need to talk about what the properties of an acid are. And you guys know this, acids taste sour. You've all had lemon juice or vinegar or something like that. You've just got that sour, tart taste. Obviously, we're not going to go and taste things like hydrochloric acid because those are bad for you. They are electrolytes when they are in solution, which most acids are. Electrolytes, remember, means that they're able to conduct an electric current, and most of them are actually very, very good electrolytes. They change the color of indicators. Remember, an indicator is simply an organic compound which changes color according to the pH of the substance it is in. Indicators are actually wonderful things, and we have a lot of natural indicators. We'll talk about this again next week. Red cabbage is a natural indicator. Black tea is a natural indicator. But depending on the pH, it changes color. Okay? And they react with bases to form a salt and water. You did a little bit of that last year where you looked at the different acid-base reactions. We're going to look at those again, and we're going to look at writing the equations for those. Bases taste bitter, and they feel soapy. And I'm pretty sure, if we're honest, okay, most of you when you were little try to eat the soap in the bath, okay, because that's what most children do, which is why I think most parents are now grateful for liquid soap, okay, and you know it's got that very bitter taste. It's a horrible taste, and they always feel soapy. Whether they're in liquid form or pellet form, they feel soapy, okay. There are also electrolytes in solution. So what that means is we've got to dissolve it first. A lot of bases are actually are solids, and then when they dissolve into a solution, they become an alkali. It's just a change in name. They also change the color of indicators. Their colors will be different to acids, okay, which is why an indicator is so nice, because it can tell you whether you have an acid or a base. Probably the best one you've ever looked at is litmus, okay, red and blue litmus paper, knowing that it goes red in an acid and blue in a base. And then, of course, just as with an acid reacts with a base reacts with an acid to form a salt and water. And remember, just so we know this, because I do, just make sure you'll recognize this, is that a salt, okay, is simply an ionic compound. That's all it is. Okay, so common acids and bases. This is actually quite important. Okay, so here we have our common acids. And guys, please, please, please learn these. You don't necessarily need to know their common names, but you do need to know the formulas and their proper names. Okay, so the first one is HCl, hydrochloric acid. Man, you've seen this lots. Used in, it's what you find in your stomach. Okay, so your stomach has got a very strong acid in it, and HCl sometimes we'll sometimes consider it as being swimming pool acid. Here's what we I'll speak English for you, shall I? Wow, it's when I try to say too much too quickly. Okay, deep breath. There we go. So we put hydrochloric acid in our swimming pools to disinfect the water, okay, to keep it nice and clean. Sulfuric acid, H2SO4, also another acid you see often. It's the acid we find in car batteries, and I really sincerely hope none of you have ever been burnt by car battery acid. It's an extremely strong acid, very, very dangerous. We then have nitric acid, okay, which is what we find in fertilizers and explosives, and it's a very important industrial acid. Ethanoic acid, also known as acetic acid, which is in vinegar. It's a very weak acid, okay? The formula here, I know it's quite long, the CH3COOH, but please learn it like that, okay? Because we're talking about the structure. When you do organic chemistry next year, you'll actually understand why it's written like that. Then we get phosphoric acid, H3PO4, which is also used in fertilizers. And I just want to add one more here, because this one I think you'll find quite interesting, is H2CO3, okay, which is actually known as carbonic acid. And now I'm going to actually hopefully not freak you out too much, but it's the acid we find in cold drink, in fizzy cold drinks. So in your favorite fizzy cold drink, you know that it's slightly acidic. In fact, in a lot of them we find phosphoric acid as well. But what makes that fizz is dissolved carbon dioxide. And the dissolved carbon dioxide forms the acid carbonic acid. And that is why fizzy cold drinks are acidic. So you've got to be careful with how many of those you drink, besides the whole thing of it rotting your teeth because of all the sugar and all those things your mother tells you. And of course, that's where the rumors come about Coke. That's saying that, you know, everyone has their rumors, and I'm sure you've watched programs that either debunk the myth or say, yes, it actually happens, where, you know, if you leave your teeth in the Coke overnight, and piece of meat, and though it's very good for marinating meat, just so you know. My brother cooks me really nice steak using that, but don't tell anyone. Family secret. Anyway, so that the reason why they say that is because it's got carbonic acid in it, okay? So there's some truth to it, but you know your teeth aren't going to rot overnight, unless of course you're drinking liters and liters and liters and liters of it, which then is actually going to affect your tummy. Okay, that's why it sometimes upsets your tummy, because it adds extra acid into your tummy. That's not good. Okay, then common bases. Now, what I really, really, really need you guys to understand here, and this is one of my pet things, and I show my own learners a very graphic video from a popular crime program of where, I'm not sure if I can say the name, on a sister channel, but this is from a couple of years ago, where one of the baddies gets pushed into a pool and he dissolves. Okay, so they're like, he dissolves. And it's quite gross, and I love watching the kids' faces go, it's great, and then I forget, oh no, age restriction, but it's fine, they're old enough. And the reason why I do this is to show them, because we all know acids are dangerous. We all understand that. We all know car battery acids. We all know hydrochloric acid. So we understand that. But then from primary school, we get taught, well, you can neutralize an acid using a base. So somewhere in the back of our minds, we're going, bases are fine. You know, if your tummy's sore, you take an antacid, the base makes it better. We're happy. But not all bases are harmless, okay? In fact, bases can be just as dangerous. And in this particular program that I show them, and I actually show them the whole thing, so science is pretty good, is he falls into a swimming pool that has been filled with sodium hydroxide. The baddie put the sodium hydroxide in the pool filter, so as the water in the pool got filtered through, instead of going through sand, it went through the sodium hydroxide pellets, dissolves all the sodium hydroxide pellets, and basically makes a big swimming pool full of a really strong solution of sodium hydroxide. And sodium hydroxide as a base pretty much attacks anything that's natural. And the really gross thing about this particular program is when they finally fish the man out the pool of what's left of him, his tackies are completely intact because they're completely synthetic. So they're fine because they're synthetic. The rest of him was natural, so there wasn't too much left. It's a bit gross, but that's besides the point. Okay, so sodium hydroxide, very, very strong base. Very, very dangerous base. Okay, so even at school, if you're doing any experiments and you do titrations or anything like that, please be very, very careful, okay? You've got to treat it with as much care as you do the hydrochloric acid. Now, sodium hydroxide, we often find in oven and drain cleaners. Okay, it's also white, it has that pungent smell. Ammonia, NH3, which we make because of the Haber process. Remember, you're going to do the Haber process till you blue in the face and you can quote it backwards. We use it in fertilizers. It's actually a very, very important part of fertilizers, okay? Then we get magnesium hydroxide. That's what we find in antacids, and it's not as strong a base, but it is still very, very strong. Sodium hydrogen carbonate. It looks almost like the carbonic acid, but now we've put the sodium with it, okay? And that's what we find in baking powder. Now, what makes that so special is because it's got the CO3, when you use baking powder, when you bake, you do it because you put it into stuff where you want it to rise. So you put it in cakes and breads and that sort of thing. And the hydrogen carbonate releases carbon dioxide. And that's what actually causes the cake to rise and that sort of thing, okay? And then there's sodium carbonate, okay, which is what we find in detergents. Okay, so all of these bases make very good cleaning agents. Okay, we don't generally use acids as cleaning agents because one of the properties I didn't put on there is that they're very corrosive. So it makes them quite dangerous. Probably the only acidic and only slightly acidic thing we use in our homes as cleaning agents is bleach. Okay, but we also know things like we don't want to use bleach on our clothes because it takes out the dye, but it also makes it very thin, and your fabrics tend to get very thin, so they tear quite easily. But most of our common bases make very, very good cleaning agents. Okay, so what we need to now look at, and yeah, we're fine. If we look at some definitions, I'm going to start with the first one with Arrhenius' definition, which I'm probably going to say wrong, and I do apologize. We all know I have an issue. Now, he came along and he made some definitions about acids and bases, and all these definitions where they start from is based on observation. Okay, so he said that an acid is any compound that dissociates, so breaks up into ions, when it is dissolved in water to produce hydrogen ions. So he said, so for example, if we look at this and we go, okay, if I take HCl and I'm going to dissolve it in water, and it's going to give me H plus ions and Cl minus ions, okay? So I'm putting it in aqueous, I'm dissolving it in water, and we're like, that's great. And you know what? Nothing wrong with this definition for acids, because when we look at our list, if you go back and look at our list of common acids, so we're going to go back to, and we look at our acids, and we look at the list, and we go, do you see that every single one of them has hydrogen in? Hydrogen, hydrogen, hydrogen. In fact, that's the important hydrogen in ethanoic acid. Hydrogen, hydrogen. So when any of these dissociate in water when they dissolve, they give us hydrogen. So we're okay with that. Nothing wrong with that. We go back here. So we're okay with that definition. If we now look at the definition of a base, is he said that a base is any compound that dissociates when it's dissolved in water to produce hydroxide ions. So for example, if I take sodium hydroxide and I dissolve it in water, it's going to become Na plus and OH minus. That's nice and easy. So that seemed to make sense, but that implies for me though that every single base needs to have an OH minus in it. And if we go back to our list of common bases and we look at this and we go, hang on, wait. First of all, no H in the ammonia, OH, no H in the sodium hydrogen carbonate, or in the sodium carbonate, but they are bases because of the way they react. So there is obviously a problem with this definition. That doesn't mean we don't learn it. It's our foundation. It's the jumping off point, okay? So Arrhenius said that any acid is a compound that when it dissociates in water will form H plus ions, and a base, when it dissociates in water, will always form OH minus ions, okay? But we've already seen there might be a bit of a problem with that definition, and I'm going to leave you with that thought while we take a short break, and then we'll solve the problem afterwards.
Okay. Mindsetters, let's take a very short break, and after the break, we will solve the problem with Tracy. So don't go anywhere. Welcome back, Mindsetters. If you have just joined us, you are with Looney and Tracy, and we're going over acids and bases, just the foundation. Tracy said earlier on, having a chilled lesson today. I'd just like to read some comments from you guys from Facebook. Yes, just very quickly. Wendy Msiza says, Tracy, you are a good teacher. You just make it easy for us. I'm already enjoying the topic. Thank you so much, Wendy. And then my Batom Bafi says, nearly missed it few. So glad you joined us, hey? And then Boykuto Ramanyane is saying, hey, can you post those common acids and bases? So I did post them on the Facebook page, guys. So hope you not panicking. And then Noah says, physics, my favorite subject. I'm in. So thank you so much, guys, for actually talking to me on the page, because sometimes I feel so lonely here when you're not saying anything. So thank you for connecting with us, and I'll take it straight back to Tracy.
Oh, thanks, Looney. Guys, just so you know, we're having a bit of Facebook is not playing with Looney today, just so you know. And she is trying to post the notes. Okay, so don't stress if you haven't got them. We're getting there. Okay, but we're getting the refresh and we're getting the comments, and we appreciate that. Thank you, guys. And I'm glad I'm making it easier for you. That's what we're here for, and hopefully it helps at the end of the year when you have to write those all-important exams, okay? Now, so when we were done just before the break, we spoke about the Arrhenius model, which said that an acid needs to produce hydrogens and a base needs to produce OH minuses. And we said, well, that's a bit of a problem because in our list of common bases, in fact, only 2 of them had OH in them. So that, of course, becomes an issue, which then means we need to go on to a second definition, and it's the Bronsted-Lowry definition, okay? And no, this is not a typo. Okay, when you see the funny O with the Bronsted, it's because I think he was Swedish. Okay, he's from Europe, so it is actually supposed to be that funny O, but if you don't use that in your exams, don't stress. Now, between the 2 of them, they came up with a new definition, which is far more broad and encompasses more. So what that means is it takes into account the fact that not all bases look the same. All acids definitely have hydrogens in them. And what they said is that acids are defined as proton donors. Okay, now first we need to talk about is, what do we mean by a proton? Now a proton in this case is a hydrogen plus ion. Because remember, hydrogen has a single little proton with its neutron, if it has a neutron, in its nucleus, and 1 little electron running around, okay? It's in its orbital. If that electron gets taken during a chemical reaction for whatever reason, it leaves what we call a little naked proton. So the little hydrogen is now a naked proton, the poor thing, okay? But actually it's a hydrogen ion. Even though it's a proton, it's the hydrogen ion, it's the hydrogen nucleus. So when we talk about it being a proton donor, we're actually talking about the hydrogen ion, okay? And if we do, as an example, H2SO4, when it reacts with water, okay, so we'll add it to water because it's easier for you to see it this way. The hydrogen goes, there we go. I'm not going to worry about balancing the equation. Hydrogen moves along, and we end up with SO4 2 minus and H3O plus ions, okay? But the hydrogen from the sulfuric acid donates and moves on to the water, okay? Now what's important here, what makes acids so dangerous? This hydronium, the H3O plus ion. That is actually the ion that makes it so dangerous. The concentration of that ion determines the pH, which you're going to do in grade 12, okay? You're going to do it with log calculations and you're going to work it out. So that little ion is the dangerous one, okay? That's the one we don't actually like. We've said hydrogen is a proton donor. Now, this is a little bit like a redox reaction, which you've learnt about before, in that if the hydrogen ion gets given away, so we give this hydrogen plus to something, something's got to take it. It can't just hang around in empty space. And the thing that takes it is the base, which means bases are proton acceptors. Okay, so your base takes the proton. It says, oh, thank you, Mr. Proton. I'll take that hydrogen. Off it goes. So, for example, if I go HCl, which we know is an acid, let's add it to sodium hydroxide, and we go along and we say, well, sodium hydroxide is a proton acceptor, so this hydrogen goes over there. This is an H plus that gets moved. The sodium hydroxide says, thank you very much, and what we get is NaCl and water. Okay, NaCl and water. The sodium has acted as a base. The hydrogen has, the HCl has acted as an acid, which is exactly what we expected. Acids are proton donors, bases are proton acceptors. Okay, but that leads us to a very important concept called the conjugate acid and base. If I have an acid and it gives away its hydrogens, it changes what it is. Okay? So, for example, and I've got a couple here. A acid, when it gives away its hydrogen, is now in a position to accept a hydrogen, so it becomes a base. So when HCl, for example, gives away its hydrogen, that hydrogen disappears, and what we're left with is Cl minus. Cl minus is its conjugate base. HCl is an acid, but it gives away its hydrogen, proton donor, becomes Cl minus. Cl minus has no hydrogens to give away. It can no longer behave like an acid because the definition says an acid must be a proton donor. There's no proton to give away, not a chance. But at Cl minus, it absolutely can accept a hydrogen. Okay, which means if I take the Cl minus and I react it with another acid, it'll take the hydrogen away from the acid. Okay, it'll take the hydrogen away. So the chlorine then becomes a base because it accepts the proton. So we're no longer concerned about the Arrhenius model. Okay, that's a model you need to learn about. But when it comes to equations and all of that sort of stuff, we have to look at the Bronsted-Lowry definition. If we consider ammonia, now ammonia is a little different, okay, in that ammonia is a base, which means it needs to accept a hydrogen, and then it forms ammonium ions, which is NH4 plus, because remember we add an H plus to it, which of course you learnt about when you did the dative covalent bond earlier this year. Okay, you would have learned how the hydronium ion is formed and how the ammonium ion is formed. Okay, in terms of the bonding. Now we're going, okay, well, where did the H plus come from? From an acid. Okay, the ammonia has acted as a base. It has taken the hydrogen, formed NH4 plus. Now we look at the NH4 plus and we go, okay, well, the nitrogen has 8 electrons around it. If we really go into its structure, remember, it looks like this. Okay, I actually do want to do the structure because I want you to see something. Okay, and this is with the dative covalent bond, but it looks like this. Now we're going to go, okay, for the ammonium, the NH4 plus, to act as a base, it must be able to accept hydrogens. We look at the structure and we go, where would that hydrogen go? There's no lone pairs. That nitrogen has four sets of electrons around it, so it's 8 electrons. It's very happy. So actually, there's nowhere for an extra hydrogen to go. There's not a chance this ammonium can act as a base. But it does have this little extra, remember it's got the little extra one, which is your dative covalent bond. And you know what? It's quite happily going to give that away, because it doesn't really like the dative covalent bond, which means the NH4 plus is now an acid, because it is in a position to give a hydrogen away. Okay? So if I start off as an acid, it will become a conjugate base, because it goes from giving a hydrogen to being able to take. If I start off with a base, it becomes a conjugate acid, because it goes from being in a position to take a hydrogen to now giving one away. Okay? Which then actually brings us to an interesting little concept called an amphilite. Okay? Now, these are, I call amphilites a little bit like a teenage girl. Looney, you're not a teenage girl anymore, so it's fine. I can say.
I know.
And right now all the teenage girls are going, that's not fair. I'm going, it's okay, don't worry. You'll understand in a second, and all the guys in your life will agree. They cannot make up their mind. Okay? So what do I mean by that? And most teenage girls, when they're with one set of friends, will go, oh, black is the new pink, or whatever it is, or pink's the new black, whatever it is, I wouldn't know. Okay? With the other group of friends, it's blue is the new black. All depends on who they're with. Okay? You all know friends like that who cannot make up their mind, and they will behave one way with a certain group of friends and one way with another group of friends. That's pretty much what an amphilite is. Okay? An amphilite is a substance that has the ability to act as an acid or a base depending on the other substance. Okay? So it is not going to go, oh, I want to act like a base. It only acts like a base if I react with an acid. It will only act like an acid if I react with a base. Water is the most common amphilite. Water just cannot make up its mind. Okay? So, for example, here we have, and I've got water here in 2 examples, and I will show you. If I react water with ammonia, okay, the water comes along. Ammonia is a base. Ammonia cannot be an acid. NH3 is a base. Will always act as a base. So what happens is the water will come along, and the water will donate its hydrogen to ammonia. Okay? Water donates its hydrogen. It has now acted as an acid, because we have that's ammonia's conjugate acid. That's water's conjugate base. OH will not give another hydrogen away, but it'll very gladly take. So because the water was reacted with ammonia, the water has acted as an acid. Okay, so here it's an acid. However, we take the same water and we react it with hydrogen cyanide, an unusual acid, but it's still an acid. What happens here is the water goes, come hydrogen, I want you. So now the hydrogen cyanide, because it is an acid and can only act as an acid, should I make that so that you can actually read the H+? I think that's a great idea. Okay, so it donates its H+, now that we can all read what I'm trying to write. And what that means is the water takes the hydrogen. Because it takes the hydrogen, it's acting like an acid, forms H3O+. So it's acting like a base. H3O+ can only act as an acid. Okay, there's not a chance that it's going to take any more hydrogens, so it'll definitely give it away. But then my Cn minus, which is the cyanide ion, okay, and yes, by cyanide I mean the dangerous stuff that can kill you, okay, which people like to use to kill people, but we're not going to talk about that, can only act as a base. Okay, the water in this case is acting as a base because it reacted with an acid. With ammonia, it was reacting with a base, so it acted as an acid. So water is an amphilite. We say it is amphiprotic. Okay? Oh, I've got to remember how to spell this, and I'm trying to put it on the board, and I can't remember how to spell amphiprotic. I'm not going to even try to spell it for you, because that's just going to be embarrassing. You don't need to know. Okay, point is, it's an amphilite. It cannot make up its mind, but it'll deter whether it can act as either. It'll act as a base when we react it with an acid, and it'll act like an acid when we react it with a base. Water's your most common, okay, but, and you'll see when we get do the questions in the next section, that sometimes your polyatomic ions are like that. They don't know they're sitting on the fence, okay? So they're neither here nor there. But water is your most common amphibolite because it really doesn't really care whether it acts like an acid or a base. It depends on what it's acting with. Okay, so we've done a lot of theory, and I have a couple of questions. So we're going to run through some questions after the break, which will hopefully bring all of this together.
All right. Can I ask you one question?
Yes.
From Sungula Marvin Baloy, he's asking, why does an acid turn negative when it reacts with the base?
Why does an acid... That's a good question. Can
After
I
the
answer
break.
it after the break?
Okay. all
That's
right.
actually a very good question. I never
Okay.
thought of that before.
Thank
Yes.
you so much, Sungula Marvin Baloy. We will answer your question straight after the break. So Mindsetters, we will be back straight after this. Welcome back, Mindsetters. We are still dealing with acids and bases. We had a question earlier from Sungula Marvin Baloy, and he asked, why does an acid turn negative when it reacts with the base?
I like that question. So we're going to quickly look at it, sweetie. Now, remember, with an acid, it's a proton donor. So that means acids give away H plus ions, okay? That's what they give away. So if we consider something like hydrochloric acid, HCl, its ions are actually H plus and Cl minus from whole valency when we make compounds and stuff. So if I take the H plus away, all that we're left with is the negative, which is why they become negative. Even if I look at something like, say, sulfuric acid, H2SO4, okay, the H is positive, even though there's two of them, so it's H plus, but the sulfate is one of those ions you have to remember. So it's SO4 2 minus. So if I'm taking the H pluses away, all that's left are the minuses. Okay, which is why when an acid reacts with a base, the acid will become negative. Bases often become positive, okay, because they're gaining a positive and the acids are giving the positive away. So if you look at the balance of charges, it sort of makes sense that if I take the positive away, I've got to be left with negative. So I'm really hoping that solves your problem.
One more.
One more question. Okay, Luni.
Yes. Mandy Sanolivi Maketa is asking, so with these amphibolites, hydrogen is donated to a compound with a high concentration of hydrogen, if that makes sense.
Okay, I think what you're trying to ask me is, will the hydrogen always go to the compound with the most hydrogen? I think. I'm not sure you can define it like that. I'm not sure you can put that as a hard and fast rule to say with an amphibolite, it's going to act like an acid when the other thing's got more hydrogens. I would rather, and they should do this with the amphibolites, and we're going to do a question with amphibolites in a second, is rather learn that you've got to know, so if they're going to look at water, rather know what your common acids and bases are so you know what the other thing is, because that will make it easier for you, okay? Because you don't want to, I'm hesitant to put a rule when it comes to the concentration because we're not doing logs and we're not doing pH and that sort of thing. So I'm hesitant to try give you a rule that about concentration of ions. I'm not sure that really helped, but I think right now we just don't have enough information and foundation to put a rule like that in. So I would rather you learned your common acids and bases and know what they are, because then you can recognize what something like water would react as. I think that'll make it a bit easier.
Two more small questions.
Okay, two more small questions. Yes, something?
Waiskuta Ramanyan is asking, can I ask something? Does H2O act as an acid or base?
Both. It's an amphibolite.
Okay.
So it all depends. If I put H2O with hydrochloric acid, it's going to act like a base. If I put H2O with ammonia, it's going to act like an acid. It's an amphibolite. It cannot make up its mind.
Okay.
Yeah.
And then Ganye Sosibia is asking, please rectify who is donating protons to who between acid and bases?
The acid donates its proton to the base.
Okay.
Okay. So you've done redox, you learned about oxidation, and you learned that something loses electrons, that's oxidized, the reduction gains electrons, that's reduced. Same with acids and bases. Acids donate their proton, the proton that they donate goes to the base, and the base accepts their proton. We happy?
That's all. Thank you.
All right, you're welcome. So let's go to some of the questions I have for you. I think that's the first one. No, that's question 2. That won't help us. Let's start by question 1. So question 1 says, and here it's about, and hopefully this will help with some of the questions we had with the positives and stuff. Give the conjugate base for the following. So what I'm saying to you is I'm going to give you some acids, and I'm going to say to you, what is its base going to look like? It's an acid. We want to know what its base is going to look like. So that means I need to give away its hydrogen. So now we say to ourselves, okay, let's go down because I want to actually come. There we go. It's always important to talk to the board. Nitric acid, it can only give one hydrogen away. So it's an acid at the moment. It gives away its hydrogen. So that means, where's the undo? There we go. That means it becomes NO3 minus. It's only one minus because I only took away one positive. Okay, if I took away 2 positives, it would become 2 minus. So this is the acid. So here's my acid. This is my conjugate base. Okay, that's my conjugate base. So look at the next one, H2SO4. Now H2SO4 is quite special because it has the ability to give away 2 protons, okay? If it only gives away 1, which can happen, it's very unusual, but it can happen, we actually end up with HSO4 minus, okay? Why only minus 1 and not minus 2? Because we know sulfate's minus 2 because it only gave away 1 of its pluses. However, more likely is it's going to give away both its minuses, both its pluses, and it's going to become SO4 2 minus. That's its conjugate base. It's a very strong conjugate base. It's a weak conjugate base, sorry. It actually doesn't really want the hydrogens back. It's quite happy, okay? Now we've got another one, H3PO4. Now we've got 3. That means we actually can have 3 conjugate bases here because it's got 3 hydrogens to give away. So if it only gives away 1, it becomes H2PO4 minus. If it gives away 2, it becomes HPO4 2 minus. If it gives away 3, it becomes PO4 3 minus. Okay? Every time it gives away its hydrogen, it becomes more negative because it's giving away positives. Okay? In reality, when we react phosphoric acid with something, it's probably going to give away all 3 of its hydrogens and become PO4 3 minus. Okay? Doesn't often want to give away the other 2. So that means we have our acid and our conjugate base. Okay? We had acid, conjugate base. So let's find conjugate acids. Okay? So now we go, okay. First one we've got here is sodium hydroxide. And sodium hydroxide is going to gain an electron. This one's a little more difficult. Okay, so we have Na plus, OH minus. That's essentially what sodium hydroxide is made up of. And what will happen here is it's a base. It's going to act as an acid. Sorry, it's an acid. Let me start that again. It's a base which is going to take a hydrogen. A hydrogen is an H plus ion, okay? Which means if we look at the makeup of the sodium hydroxide, it's got to go to the OH. The sodium can't take it because the sodium is already positive, and positive won't go to positive. You know that. So it has to go to the negative, which means this becomes H2O. Okay? H2O here is now an acid. Sodium plus cannot act as an acid. Not a chance. An acid has to have a proton to donate. It has to have H plus ions. There are none in the Na plus, okay? So this is my base. This is its conjugate acid. Okay, it's conjugate acid. Please, this one's a little more difficult to see than with the acids. Potassium hydroxide, same thing. Potassium hydroxide is K plus ions and OH minus ions. So now we're going to say to ourselves again, we need to accept a proton, which means we need to accept an H plus ion. So we look at the makeup of the base and we go, not a chance. K plus cannot become KH. All right, does not exist as we've got it there. OH minus absolutely can take it, forms water. H2O, that's its conjugate acid. Okay, and I've said to you earlier today, of course, that water is an amphiolite. Here, it's making up its mind. Here it's going, I want to be an acid. Okay, because it is the conjugate of a base. Okay, next one. MgOH2, sorry. So if we go, let's look at it again. Well, that's Mg2 plus, even more positive than the last ones we looked at. And we have OH minus. I know there's two of them, but that actually doesn't make a difference here. And we've got to say to ourselves again, which of those are in a position to accept the hydrogen? Which of these are going to take the hydrogen, which would be the water, and then what is in the has the ability to give it away. Okay, so it's not the Mg2 plus. That is not an acid. Not a chance can that be an acid. All right, so be careful with your bases. Finding conjugate acids are far easier than finding conjugate bases from your acids are far easier than finding your conjugate acid from a base. Simply because often with the bases, it's going to create water. Okay, so be careful with that one. All right, that leaves us with question 3. Now we have to identify the conjugate acid-base pairs, okay? So in other words, first thing we're going to do is we're going to say, okay, let's look at first identifying the acid and the base originally, and then we're going to find its conjugate, okay? Hydrochloric acid is an acid. We're happy with that. I'm just going to call it an A. We're going to make our life easier. Sodium hydroxide is a base. Oops. Let me make it look like a B. Is a base. No one should hopefully be screaming at the TV just yet. Now I'm going to go, okay, what is actually happening here is the HCl is donating its proton to the NaOH. Okay. So we're happy with that. On the other side, we've got to now go, all right, how do we recognize which is the acid, the base? And we go, okay, the HCl would have broken up. Remember, sodium hydroxide can be sodium chloride, sorry, can be NaCl, Na plus Cl minus, and water is H2O. If we look at the NaCl and we go, okay, for it to be a acid, we need to have a hydrogen present. There is no hydrogen in NaCl. It is so not an acid. It is definitely a base. It has Cl in it. That means it's paired with the HCl. Okay? Water, because it's now working with the NaCl, it's definitely in a position to give away a hydrogen. It's become an acid. So it is the sodium hydroxide's conjugate acid, which we've actually just done. We just looked at the conjugate base acid to sodium hydroxide. Let's look at H2SO4 and KOH. Well, the H2SO4 will give its hydrogen to the potassium hydroxide. So sulfuric acid is the acid, potassium hydroxide is the base. And we go, well, all right, we've just done this, that we know that potassium hydroxide's conjugate acid is water. So they will go together, which then means that sulfuric acid's conjugate base is the potassium sulfate. Okay? The potassium sulfate is in a position to accept hydrogens if the potassium goes away. Okay? Which means if it can accept hydrogen, H plus ions, it is a base. Last one, and I'm hoping by now you guys are starting to see the trend. Let's just take it so I've got a little bit more space. Okay? And let's change color. So, sodium hydroxide, that's a base. Nitric acid is an acid. We just did sodium hydroxide. And we go, no, we know this. We know that for the base, because it takes the hydrogen, remember it's going to take the hydrogen from the from the nitric acid. That's going to give me water. Water here is going to be an acid. Okay. We're going to take that away. It's really just not playing ball with me, so it's going to be an acid. So sodium hydroxide's conjugate acid is water, which means nitric acid's conjugate base is sodium nitrate. Please, these questions have been put the way they are because I do not want you to learn that first goes with first, second goes with second. Okay? Because that's what happened in the first two. First one on the left, first one on the right, second one on the left, second one on the right. Please don't learn that. Okay? Because we don't have to write it in that order. And you can see here that's not what happened. Okay? So please, 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 please don't learn that. It's very, very important. Last question that I have. Now I say to you, using relevant reactions to show that the following are amphiolites. In other words, I need to give an equation, so we're going to give two equations. One, where I show my HCO3, which is the hydrogen carbonate ion, acting as a base. One, where I show it acting as an acid. Easiest thing to do is let's think about the situations where this is going to happen, okay? So in order for it to act as an acid, I need to react it with something that's going to take a hydrogen. Easiest one is if I go HCO3 and I say let's react it with an OH minus ion. Now that OH minus ion could be attached to sodium or potassium or whatever. I'm not concerned about that, which means this hydrogen is going to go, there we go, let's go to the OH minus ion. The OH minus ion is a base without a doubt. So we end up with CO3, 2 minus, and water. The OH minus desperately wants a hydrogen. If I take the HCO3 minus, and now I react it with H3O plus, which is absolutely an acid, the H3O plus is going to go, no, here you go. You have my extra hydrogen because it's so friendly. Okay. And we end up with H2CO3 and water. Okay, so whenever we need to prove that it's an amphiolite, we need to react it with something we know is either an acid or a base. So just quickly, because Looney, do you have any questions for me?
Yes, there's one question here.
Okay, just let me answer the question and then I'll come back to the last one. Yeah.
Okay. I hope you understand it because it's a bit confusing.
Okay.
Do we have to use the periodic table to determine if a reactant is an acid or a base, or can we see that just by looking at the reactions? And then here's the word that I don't understand. Conjugate pairs.
Okay, for the conjugate acid-base pairs,
yes.
You don't need the periodic table at all. Okay, you need to be able to recognize it from the reaction. Okay, the periodic table's not going to help you here at all. Yeah.
Two more.
Yes.
Philip is asking, are these reactions reversible?
Most of them are. Not all of them, but most of them are, yes.
And then Janky Paul Senatla is asking, what is the formula of MgCl?
You got it there, MgCl.
So maybe...
I'm confused. I think if it's MgCl2 maybe, I don't know.
He just wrote MgCl.
I don't know what the question means. But I think we ran out of time for 2 seconds. But
okay.
I'm going to leave with you guys just quickly. Prove that HSO4 is a acid or a base. Reacted with OH minus, acts as a base. So acts as an acid. React with H3O minus, acts as a base. We'll make sulfuric acid or SO4 2 minus. Okay. And I think we've run out of time.
Yes.
So guys, thank you. Next week we're going to do titrations and then we're going to do calculations. But hopefully we've set a nice foundation.
Yes. Mindsetters, I hope you guys enjoyed the show and you had fun with Tracy and I. And we'll see you same time, same place next week. Until then, it's a goodbye from us.
acidic, so you've got to be careful with how many of those you drink, besides the whole thing of it rotting your teeth because of all the sugar and all those things your mother tells you. And of course, that's where the rumors come about Coke. That's saying that, you know, everyone has their rumors, and I'm sure you've watched programs that either debunk the myth or say, yes, it actually happens, where, you know, if you leave your teeth in the Coke overnight and piece of meat, and though it's very good for marinating meat. Just so you know, my brother cooks me really nice steak using that, but shh, don't tell anyone. Family secret. Anyway, so the reason why they say that is because it's got carbonic acid in it, okay? So there's some truth to it, but you know, your teeth aren't going to rot overnight. Unless, of course, you're drinking liters and liters and liters and liters of it, which then is actually going to affect your tummy. Okay, it's why it sometimes upsets your tummy, because it adds extra acid into your tummy. That's not good. Okay. Then, common bases. Now, what I really, really, really need you guys to understand here, and this is one of my pet things, and I show my own learners a very graphic video from a popular crime program of where, I'm not sure if I can say the name, on a sister channel, but this is from a couple of years ago, where one of the baddies gets pushed into a pool and he dissolves. Okay, so they're like, he dissolves. And it's quite gross, and I love watching the kids' faces go, ooh, it's great. And then I forget, oh, no, age restriction, but it's fine, they're old enough. And the reason why I do this is to show them, because we all know acids are dangerous. We all understand that. We all know carbohydrate acids. We all know hydrochloric acid. So we understand that. But then from primary school, we get taught, well, you can neutralize an acid using a base. So somewhere in the back of our minds, we're going, bases are
Welcome to it, grade 11 Mindsetters. It is your time for physical sciences, and you're hanging out with Looney and Tracy. How are you, Tracy?
good, and you?
It's been forever.
It does seem like it. Where have you been? I've been here. Where have you been?
I've been multitasking with the other days and all the
Fun.
other.
That's okay. You can like that.
So what are we doing for the grade 11 today?
Today we're going to start our acids and bases series. We're going to do this for 3 weeks. We're very excited, but today we're going to lay a bit of foundation, do some what's the word, terminology, do some definitions, basic stuff. So it's compared to some weeks, it's quite a nice
Chilled session.
chilled week. Yeah.
Okay. Grade 11s, you heard it's a chilled. You saw Tracy, she's like, it's a chilled lesson today. You're just doing the foundations of acids and bases. Remember to hit us up on Facebook. Our page is facebook.com/learnextra. You can also follow us on Twitter, and we'll follow you back at learnextra. And you can download the show notes, the videos, the schedules on learnextra.co.za/live. So with all that said, I'll hand it over back to Tracy.
Oh, thank you, Lee. Okay, well, guys, as I said earlier, we're doing acids and bases, which is really nice. And what we're going to do today is we're basically going to look at the properties of acids and bases. Shouldn't be anything new, hopefully, because you've been doing this since grade 9. We're going to list some of the common acids and bases. It's really, really important that you know their formulas. We're going to do some definitions of acids and bases. There's actually a couple. Most parents are now grateful for liquid soap, okay? And you know it's got that very bitter taste. It's a horrible taste. And they always feel soapy. Whether they're in liquid form or pellet form, they feel soapy, okay? There are also electrolytes in solution. So what that means is we've got to dissolve it first. A lot of bases are actually are solids, and then when they dissolve into a solution, they become an alkali. It's just a change in name. They also change the color of indicators. Their colors will be different to acids, okay, which is why an indicator is so nice, because it can tell you whether you have an acid or a base. Probably the best one you've ever looked at is litmus, okay, red and blue litmus paper, knowing that it goes red in an acid and blue in a base. And then, of course, just as with an acid reacts with a base reacts with an acid to form a salt and water. And remember, just so we know this, because I do, just make sure you'll recognize this, is that a salt, okay, is simply an ionic compound. That's all it is. Okay, so common acids and bases. This is actually quite important. Okay, so here we have our common acids. And guys, please, please, please learn these. You don't necessarily need to know their common names, but you do need to know the formulas and their proper names. Okay, so the first one is HCl, hydrochloric acid. Man, you've seen this lots. Used in, it's what you find in your stomach. Okay, so your stomach has got a very strong acid in it, and HCl sometimes we'll sometimes consider it as being swimming pool acid. Okay, that's what we I'll speak English for you, shall I? Wow, it's when I try to say too much too quick. And we're going to talk about why we don't use them, why we don't use one anymore. We're going to talk about why we do use the others. We're going to discuss the concept and look at conjugate acid-base pairs. That's really, really important. And we're going to discuss the concept of an amphibolite. So we're really just laying the foundation, doing some basic work. In the next couple of weeks, we'll look at titrations and calculations. But today, we're just really laying a foundation, okay? So the first thing we need to do is we need to talk about what the properties of an acid are. And you guys know this, acids taste sour. You've all had lemon juice or vinegar or something like that. You've just got that sour, tart taste. Obviously, we're not going to go and taste things like hydrochloric acid because those are bad for you. They are electrolytes when they are in solution, which most acids are. Electrolytes, remember, means that they're able to conduct an electric current, and most of them are actually very, very good electrolytes. They change the color of indicators. Remember, an indicator is simply an organic compound which changes color according to the pH of the substance it is in. Indicators are actually wonderful things, and we have a lot of natural indicators. We'll talk about this again next week. Red cabbage is a natural indicator. Black tea is a natural indicator. But depending on the pH, it changes color, okay? And they react with bases to form a salt and water. You did a little bit of that last year where you looked at the different acid-base reactions. We're going to look at those again, and we're going to look at writing the equations for those. Bases taste bitter, and they feel soapy. And I'm pretty sure, if we're honest, okay, most of you when you were little try to eat the soap in the bath, okay, because that's what most children do, which is why I think, Becky, okay, deep breath, there we go. So, we put hydrochloric acid in our swimming pools to disinfect the water, okay, to keep it nice and clean. Sulfuric acid, H2SO4, also another acid you see often. It's the acid we find in car batteries, and I really sincerely hope none of you have ever been burnt by car battery acid. It's an extremely strong acid, very, very dangerous. We then have nitric acid, okay, which is what we find in fertilizers and explosives, and it's a very important industrial acid. Ethanoic acid, also known as acetic acid, which is in vinegar. It's a very weak acid, okay? The formula here, I know it's quite long, the CH3COOH, but please learn it like that, okay? Because we're talking about the structure. When you do organic chemistry next year, you'll actually understand why it's written like that. Then we get phosphoric acid, H3PO4, which is also used in fertilizers. And I just want to add one more here, because this one I think you'll find quite interesting, is H2CO3, okay, which is actually known as carbonic acid. And now I'm going to actually hopefully not freak you out too much, but it's the acid we find in cold drink, in fizzy cold drinks. So in your favorite fizzy cold drink, you know that it's slightly acidic. In fact, in a lot of them we find phosphoric acid as well. But what makes that fizz is dissolved carbon dioxide. And the dissolved carbon dioxide forms the acid carbonic acid. And that is why fizzy cold drinks are